So water is a really cool substance. Water can act as an acid, and it can also act as a base. And we have a special word for that, amphoteric. Think about amphibians. Where do amphibians live? They live in the water and on the land. Of course, you can't live in both at the same time, so yeah, they live on the water, in the water or on the land, right? An amphoteric substance can be an acid or a base. It can act as either one. You can't be both at the same time. But it behaves either as an acid or at a base. I don't remember what's coming up on the next slide, but let's look at this. So, pardon me? It's a mystery, yes. It adds a little excitement to my life to not actually look at the slides before I lecture on them. I think that might be the underlying reason why I'm often late, too, because if you don't leave quite enough time to get there, then you get this adrenaline rush from hurrying, right?
Oh, yeah. I get that like every Monday, Wednesday, Friday.
Yeah.
Except for
I have 15 minutes from my driveway to my classroom.
I know.
Okay, so this is what can happen. This is what can happen in water, which is really kind of crazy to think about. Two water molecules. One can act as an acid and the other can act as a base. And so this one can say, hey, give me one of those hydrogen ions. And that one will say, oh, okay. And so this one becomes a hydronium ion, and the other one, by giving up its hydrogen ion, becomes a hydroxide ion. That's crazy, huh? Why would that happen? Well, it happens to a very, very, very small extent. And this is the expression that tells us how much water does this. This is an equilibrium constant for this reaction, and we haven't studied that. But what this tells us is that the concentration of the hydrogen ion, which is just a shorthand way of writing hydronium ion, the concentration, the molar concentration of hydrogen ion times the molar concentration of hydroxide ion in pure water equals 1 times 10 to the minus 14. That's a very, very small number. And so if we look at the arrow here, the arrow really is like that. Little teeny arrow going forward. It goes forward a little bit. And so it's really more like these two mothers, and they each have a baby, because they both have hydrogen ions. And one says, hey, could you hold mine for just a minute? I need to pick something up. And then they take it back. And so the hydronium ions and hydroxide ions in pure water, the concentration of them at any given time is very, very low, and yet they are there. So no matter what the solution contains, the product of the hydrogen ion concentration and the hydroxide ion concentration is always going to be this number. And that's a little beyond what we've talked about, but you'll just have to take my word for that. So we have three possible situations. Pure water, or a neutral solution, is where the hydrogen ion concentration is equal to the hydroxide ion concentration. Because if we think back to that equation, which is gone now, I can write it again though. So 2H2O actually let's just do it this way. No, let's not do it that way. I don't know what I'm doing. No, I really don't know what I'm doing. It was not a good night for sleeping. Andrew didn't want to wear a pajama shirt because he wanted to wear his Ninja Japanese Dragon pajama pants, and he doesn't have a Japanese Dragon pajama shirt. I don't know why he all of a sudden cares about matching his pajamas. He doesn't care about matching anything else.
What if he's attacked at night?
I know, you have to look good, right? So anyway, but he slept without a shirt on. I said, you're going to be cold. He says, but I'll be under the blanket. Yeah, well, he's 4, and that's a little blanket that he insists on sleeping with. So the blanket keeps coming off, and he keeps waking up, and then I have to go in there. And so it was not a good night for sleeping.
huge blink.
Well, yeah, but there's always something. So in this equation, if we just have pure water, could we ever have different amounts of hydronium ion and hydroxide ion concentrations? Could you get one of these without getting one of those? No. So they have to be equal. So when they are equal, that's a neutral solution. If you put an acid into the water, the acid forms hydronium ions. So that's going to increase the concentration of the hydronium ions, and the concentration of the hydroxide ions is not going to increase. And so that's an acidic solution where the concentration of hydrogen ions is greater than hydroxide ions. And a basic solution is the opposite, because the Arrhenius definition of the base was that it produces hydroxide ions in solution. So you put a base in, then hydroxide ion concentration is higher, right? So if the hydrogen ion concentration is less than the hydroxide ion concentration, then we have a basic solution. People's eyelids are getting heavy. It's not just him. It's not just him. There's others too. I won't name names or point fingers. It's okay. It's not exactly thrilling stuff.
Would you repeat that last part about the basic solution?
Sure, I can repeat that about the basic solution. At least I think I can. Oh, good. It is Friday. So in a basic solution has more base in it. And so the hydroxide ion concentration is going to be larger than the hydrogen ion concentration.
You actually add more to the base.
Right. So I think a good way to remember these three conditions is, so pure water, the ions that are present come from the water molecules, and when you make one, you get the other one. And so they have to be equal. That's neutral, pure water. If you add an acid to the solution, what do acids do? Acids produce hydrogen ions. The hydrogen ion concentration is going to go up. There's nothing there to make more hydroxide ions, and so you have an acidic solution when you add an acid. If you add a base, you get a basic solution. What do bases do? Bases form hydroxide ions. So the hydroxide ion concentration is higher. Does that make sense? Mm-hmm.
So one produces one more of the other, and the other produces more of the other.
When you add a base,
What part of the both makes it exclude the other?
well,
Depends on the reactants, right?
yeah, it depends on the substance. So like sodium hydroxide, when you put that in water, it ionizes and forms sodium ions and hydroxide ions. It forms hydroxide ions. That increases the concentration of the hydroxide ions because you actually were just adding hydroxide ions. It's more complicated than this, but this is enough to understand. And if we add something like HCl, which is a strong acid, that ionizes and forms H plus and Cl minus. Well, I've increased the hydrogen ions. Okay? So that's a good question. Pardon me?
I think it's confusing because the first time we're using water as the example.
Oh, it was confusing because of the water.
It was like even.
Right. And I was showing you the water because I wanted to show you that these ions are present in pure water and they have to be equal in the pure water. The acidic solution, the basic solution, now we're adding something else. It's not just the pure water becoming acidic or basic. That doesn't happen. So here's a multiple choice question. In an acidic aqueous solution, which statement below is correct? Well, could D be correct? Could it possibly be D? That the hydrogen ion concentration is less, not in an acidic solution. So we can just rule that one out right away. And so what is this 10 to the 7th minus 7th molar thing? Well, yeah, when H plus equals OH minus, And when we put the brackets around, it means the molar concentration of whatever's inside the brackets. Those are going to equal 1.0 times 10 to the minus 7. Because 1.0 times 10 to the minus 7 times 10 to the minus 7, if you multiply those, you get 10 to the minus 14. So this is the concentration in pure water. So A then is saying that the concentration of the hydrogen ion would be less than what it is in pure water. Is that true in an acidic solution? No. How about B? The hydrogen ion concentration is greater than what it would be in pure water. That is true. And then let's just double check this other one here. That the hydroxide ion concentration would be greater than what it is in pure water. No, that would be a basic solution, wouldn't it? So if the hydrogen ion concentration is greater than 10 to the minus 7th molar, it's acidic. If the hydroxide ion concentration is greater than 10 to the minus 7th, it's basic.
So that equation, like 10 to the minus 7,
Mm-hmm.
is that, is this neutral on the pH scale, right?
It's neutral, yeah.
And that is what number?
So in pure water,
32, right?
we have this constant here. It equals 1 times 10 to the minus 14th, or 10 to the minus 14. If H plus and OH minus are equal, then they are each the square root of 10 to the minus 14, which is 10 to the minus 7. What happens is when you add acid, and we haven't talked about equilibria, but when you add acid, it causes the reaction to shift a little bit. Some of that added acid will react with the hydroxide ions and make them go lower, and this will always be true. When you add acid, if you add base, this relationship is always true. It's kind of weird. It's like a sort of a yin-yang thing. It's a little bit like throwing a rope over a beam. And if you pull down and make one end longer, the other end gets shorter. And if you pull this one down, the other one gets shorter. And if they're in the middle, they're at 7. But if you pull this one down to minus, if you pull this one down to 10, then that one goes up to 3. So they go back and forth like that. Or 4, it would be 4 now. Anyway. So in an aqueous solution in which the hydroxide ion concentration is 2 times 10 to the minus 10, what's the hydrogen ion concentration? Well, we have to use this equation up here. So we're going to have to do some math. Okay. Whoops, that's not what I wanted to do. So we're trying to find the H plus. So we want to divide this side by OH minus, and then we have to divide this side by OH minus also. These guys cancel out. And so we end up with an equation that says that the hydrogen ion concentration is equal to 1.0 times 10 to the minus 14 divided by the hydroxide concentration. We're given the hydroxide ion concentration, so we'll plug that in. 1.0 times 10 to the minus 14 will divide by 2.0 times 10 to the minus 10. And here you need to be able to do this on your calculator. Scientific notation. I don't want to do that on my phone. I want to do it on my calculator.
How did you get OH?
The OH concentration was given.
Right, how did you get the 2.0?
It's given. Right here.
Oh.
I kind of obliterated it here, but it's still in there hiding. So you have to use the EE button correctly on your calculator. You're going to end up with the wrong answer. So go 1 EE minus 14 divided by 2 EE minus 10. And that's going to be 5 times 10 to the minus 5. And the concentration will be moles per liter. These calculations, the units are kind of odd because kW is a unitless quantity. And so I know I've been harping on you all semester, put in the units, put in the units. This is a place, just don't put in the units. At the end, the concentration is always in molarity. So then what's the correct answer? It's C, right? Well, C or D. Is this solution going to be acidic or basic? Acidic. Okay, because let's look at the hydrogen ion concentration. Compare it to neutral, which would be 10 to the minus 7. Is 10 to the minus 5 greater than 10 to the minus 7? It is. So this has a higher hydrogen ion concentration, so it's an acidic solution, and so this is the correct answer. They both have 5 times 10 to the minus 5, but this one has that answer correct.
Can't you pick your answer based on like what you're finding? Well, 'cause it says H plus equals, so then wouldn't it be acidic? Or
Well, but if all aqueous solutions have H plus present, it's just whether it's more or less than 10 to the minus 7. So there are two things. We did narrow it down to these two based on that concentration that we calculated. But then they're asking us also, is that acidic or basic? And so that's the difference between those two answers. Any other questions? I hope this is the last slide. Yay!